The ejection system of a modern fighter jet is often described as a miracle of last resort. A compact, brutal machine embedded inside a cockpit measured in centimeters, designed to turn certain death into a survivable event in less than half a second. To the pilot who straps into the seat, it represents confidence made physical: layered composites, hardened steel rails, rocket motors calibrated to millisecond precision, and a canopy engineered to shatter or vanish on command. From the outside, the aircraft appears invincible. Carbon fiber skins blend seamlessly into titanium frames. The canopy gleams, transparent and flawless, a pressure vessel that must resist bird strikes at supersonic speeds and thermal shock from high-altitude flight. Nothing about this system looks fragile. Everything about it suggests absolute control. At the heart of this confidence sits the ejection seat itself, a self-contained escape capsule bolted into a machine capable of pulling 9 times the force of gravity. The seat is not merely furniture. It is a structural component, tied into the airframe through load paths carefully calculated to survive the violent acceleration of a 0-0 ejection. Inside it are sequencers, pyrotechnic cutters, rocket packs, drogue chutes, and survival systems, all stacked with almost no margin for error. Engineers speak of it in reverent terms. It is tested on sleds, fired from towers, frozen, baked, vibrated, and slammed with forces that would destroy almost anything else designed by human hands. On paper, it is flawless. The canopy above the pilot reinforces that illusion. Modern fighters rely on advanced transparencies made from stretched acrylics, polycarbonates, or laminated composites, sometimes coated with thin metallic films for radar and thermal control. These canopies are pressurized shells, bearing differential loads at altitude while remaining optically perfect. They are bonded to frames with adhesives chosen for flexibility, strength, and resistance to ultraviolet degradation. In an emergency, they must either fragment cleanly under explosive cords or be jettisoned into the slipstream without striking the pilot. The sequence is choreographed like a ballet of violence. First the canopy, then the seat, then the parachute. Each step assumes the previous one worked exactly as intended. This architecture of confidence is what allows pilots to fly at the edge of physics. When a jet climbs vertically through thinning air or dives toward the ground at transonic speed, the pilot trusts that if the machine betrays them, the seat will not. That trust is absolute. It has to be. There is no time in an emergency to question metallurgy, adhesives, or fatigue curves. The system either works or the pilot dies. Yet buried deep within this apparent perfection lies a reality engineers have learned repeatedly and painfully. No structure is immune to time, heat, vibration, and stress. The ejection system is not separate from the aircraft's weaknesses. It is bound to them. Every flight cycle loads the seat rails. Every pressurization cycle strains the canopy. Every high-speed run heats the transparencies unevenly, expanding one layer faster than another. These effects are microscopic, invisible to the naked eye, and easy to dismiss in early design reviews. After all, safety factors exist. Margins are generous, or so it seems. The hidden flaw often begins with geometry: a sharp corner in a metal fitting beneath the seat, a slight mismatch in stiffness between the canopy frame and the transparency, a bolt hole drilled a fraction of a millimeter off-center, creating a stress concentration no one modeled in full fidelity. Under static loads, nothing happens. Under the controlled violence of test rigs, the system passes. But flight is not a single load. It is thousands of cycles, each one adding a tiny insult to the material. Consider the seat rails that guide the ejection seat upward. They are typically machined from high-strength steel or titanium alloys, chosen for their toughness and resistance to fracture. But they are also subjected to constant vibration from the airframe, especially in fighters where engines are rigidly mounted close to the cockpit. At certain frequencies, micro-movements occur between the seat and the rail. Over time, this fretting can damage protective coatings and expose raw metal. Once exposed, the surface becomes vulnerable to corrosion, especially in naval aircraft operating in salt-laden air. The engineers at the drawing board knew about corrosion. They specified coatings, sealants, inspection intervals. What they underestimated was the interaction between corrosion pits and cyclic loads. A pit only microns deep can act as a crack initiator. Under repeated stress, that pit becomes a microscopic crack. And once a crack exists, the physics of fracture mechanics takes over, indifferent to intent or reputation. The canopy suffers its own slow degradation. Transparent materials behave very differently from metals. They creep under load. They are sensitive to temperature gradients. At high altitude, the outer surface of the canopy can be at sub-zero temperatures, while the inner surface is warmed by cockpit air and solar radiation. This creates thermal stresses across the thickness of the material. Over years, these stresses can cause crazing, networks of tiny cracks that scatter light and weaken the structure. Individually, they are harmless. Collectively, they reduce the canopy's ability to withstand sudden loads, such as those imposed during a high-speed ejection. Adhesives, often seen as secondary elements, become critical players in this drama. The bond between canopy and frame must flex without failing, yet remain strong enough to transfer loads. Adhesives age. They absorb moisture. They harden or soften depending on chemistry and environment. A bond line that was perfect at delivery may be compromised a decade later, its properties drifting outside the assumptions baked into the original design. None of this announces itself with alarms or warning lights. There is no cockpit indication for adhesive embrittlement or subcritical crack growth. Maintenance crews inspect what they can see, guided by manuals written years earlier. They look for visible damage, discoloration, looseness. But the most dangerous changes occur beneath the surface, at scales measured in grains and dislocations. The invisible degradation continues, flight after flight. Each supersonic dash heats the canopy unevenly. Each carrier landing slams the seat into its rails with brutal deceleration. Each pressurization cycle stretches the transparency and relaxes it again. Inside the metal and polymer, cracks grow by fractions of a millimeter. They pause, then advance again. The system remains functional, passing pre-flight checks, inspiring confidence. Until one day, the margin is gone. The catastrophic sequence does not begin with drama. It begins with a decision, an engine flameout, a loss of control, a warning tone that leaves no room for recovery. The pilot reaches for the ejection handle, a motion drilled into muscle memory. In that instant, the entire escape system is called upon to perform as designed, without hesitation. Explosive charges fire to fracture the canopy or sever its attachments. But a canopy weakened by years of thermal stress does not behave as predicted. Instead of fragmenting cleanly, it shatters irregularly, leaving jagged sections momentarily in place. The timing of the sequence, calibrated for a pristine structure, is now off by milliseconds. That delay is enough. The seat rockets upward along rails that have quietly suffered from fretting and corrosion. Under the immense acceleration of the ejection rocket, a crack that had been dormant for years suddenly propagates. Stress intensity skyrockets. The rail fractures, twisting the seat slightly off-axis. The pilot's body, already experiencing extreme G-forces, is now subjected to asymmetrical loads. Air rushes into the cockpit as pressure equalizes violently. The shock wave slams into the seat and the pilot. Debris from the canopy strikes the helmet. The sequencer continues its logic, blind to the chaos, deploying stabilization devices designed for a cleaner exit. In fractions of a second, the difference between survival and catastrophe is decided by the integrity of components measured in millimeters. Sometimes the system still saves the pilot, battered but alive. Sometimes it does not. In other cases, the failure is discovered not through tragedy but through chance. A cracked rail found during a deep inspection, a canopy delaminating unexpectedly in a hangar. The aircraft is grounded. Then another. Then an entire fleet. The immediate aftermath is shock. A machine trusted by pilots and engineers alike is suddenly suspect. Operational commanders demand answers. Fleets are stood down. Missions are canceled. The cost of inaction now outweighs the cost of investigation. Forensic teams descend on the aircraft like pathologists. Every component of the ejection system is cataloged, photographed, and measured. Metallurgists cut samples from failed rails, polishing them to mirror finishes to study under microscopes. They find beach marks, telltale signatures of fatigue crack growth. Polymers from canopies are analyzed for molecular weight changes. evidence of ultraviolet degradation and thermal aging. Adhesive bonds are peeled apart to examine failure modes: cohesive, adhesive, or mixed. The root cause emerges slowly, often uncomfortably. The design met the requirements. The tests were passed. But the real world introduced variables that were underestimated or ignored. The engineers had assumed certain load spectra. The aircraft flew harder missions. They assumed inspection intervals were sufficient. Aging mechanisms proved faster. They assumed safety factors would cover uncertainties. Physics disagreed. This realization reshapes engineering doctrine. New inspection techniques are mandated. Ultrasonic scans of seat rails, enhanced visual criteria for canopy crazing, stricter limits on adhesive life. Materials are reconsidered. Sharp corners are eliminated. Coatings are improved. Thermal models are refined. Certification standards are rewritten to account for aging, not just initial strength. The legacy of such failures is not limited to one aircraft. It ripples across the industry. Ejection seats are redesigned with greater tolerance for misalignment. Canopy systems incorporate redundancy and improve fracture control. Engineers become more humble, more cautious about declaring any structure invincible. In the end, the escape system of a modern fighter stands as a paradox. It is both one of the most reliable life-saving devices ever created and a reminder of how unforgiving physics can be. It embodies human ingenuity and human arrogance in equal measure. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault. The investigation rarely stops at the first fracture. Once confidence is broken, engineers begin to trace the failure backward in time, reconstructing years of invisible damage that led to that single moment. In the case of modern ejection systems, this forensic rewind often reveals a chain of assumptions layered one on top of another, each reasonable in isolation, but dangerous in combination. At the core lies material selection. High-strength alloys dominate ejection seat structures because they allow compact designs capable of surviving extreme loads. Titanium alloys, maraging steels, and precipitation-hardened stainless steels are chosen for their impressive yield strength and fracture toughness. On certification charts, they look nearly indestructible. But high strength comes with a trade-off: sensitivity. These materials are less forgiving to surface damage, corrosion pits, and manufacturing defects than lower-strength steels. A microscopic scratch introduced during assembly, polishing, or maintenance can become the birthplace of a crack. Engineers understand this academically. They model stress concentrations using idealized geometries, smooth surfaces, and controlled environments. What is harder to model is reality. In service, seat rails are exposed to vibration spectra far more complex than those reproduced in test labs. Fighter aircraft operate across envelopes that include sustained high-frequency vibration from engines, low-frequency buffet from high angle of attack flight, and impulsive loads from carrier landings or rough field operations. Each regime excites the structure differently, producing microslip at interfaces never intended to move. That microslip is insidious. Known as fretting, it occurs when two components in contact experience very small relative motion under load. Fretting damages protective oxide layers and coatings, exposing fresh metal. Once exposed, that metal reacts with oxygen and moisture, forming oxides that occupy more volume than the base material. This expansion increases local stresses, accelerating crack initiation. None of this is dramatic. It unfolds silently, beneath layers of paint and composite fairings. Thermal effects compound the problem. Modern fighters push materials to temperature regimes once reserved for experimental aircraft. During supersonic flight, aerodynamic heating raises skin and canopy temperatures significantly. When the aircraft slows or descends, rapid cooling follows. These thermal cycles induce expansion and contraction in every component, but not uniformly. Dissimilar materials expand at different rates. Steel rails are constrained by aluminum or composite structures. Canopies bonded to frames experience shear stresses at adhesive interfaces as temperatures swing. Over thousands of cycles, these stresses accumulate damage. Polymers craze. Adhesives lose elasticity. Metals experience low cycle fatigue at stress levels well below their ultimate strength. Engineers sometimes refer to this as the tyranny of cycles. the realization that even modest stresses, repeated often enough, will eventually cause failure. The hidden flaw, then, is rarely a single mistake. It is an underestimation of how these mechanisms interact over time. Design reviews focus on peak loads, the violence of an ejection, the bird strike, the maximum pressurization differential. But the aircraft spends most of its life far from those extremes, accumulating damage in small, unremarkable increments. This is where hubris enters, the belief that if a system survives the worst case, it will surely survive everything else. Flight testing reinforces this illusion. Prototypes are young, materials are pristine, coatings are intact, adhesives are fresh, early data looks excellent, confidence grows, production ramps up. By the time the fleet ages into the danger zone, the original designers may have moved on, their assumptions frozen into certification documents. When degradation reaches a critical point, the system becomes brittle in a metaphorical sense. Not brittle in the classic material definition, but brittle in margin. There is no longer room for error. A slightly off-nominal event, a hotter than expected flight, a harder than usual landing, becomes enough to push the structure past its limit. The catastrophic sequence that follows is governed by physics, not intent. Crack propagation accelerates dramatically once a critical length is reached. Stress intensity at the crack tip increases nonlinearly. In metals, this can transition from stable growth to rapid fracture in an instant. In polymers, crazes coalesce into cracks that unzip under load. Adhesive failures propagate along bond lines, peeling structures apart. During an ejection, these processes unfold faster than human perception. The seat rocket produces accelerations exceeding 20 g in milliseconds. Loads spike along rails, through attachment lugs, into the airframe. Any asymmetry becomes amplified. A fractured rail does not merely fail, it redirects loads unpredictably, introducing bending moments never accounted for in design. The canopy, weakened by years of service, may not clear the cockpit as intended. Fragmentation patterns change. Instead of shattering into small, aerodynamically benign pieces, larger fragments linger in the airstream. These fragments can strike the seat, the pilot, or the stabilizing devices meant to orient the seat. The sequence is unforgiving. There is no pause to adapt. When such a failure occurs, survival becomes a matter of probability rather than design. Some pilots live because the failure is partial, because the crack arrests, because the fragment misses by centimeters. Others do not. To the outside world, the outcome looks arbitrary. To investigators, it is the final data point in a long, deterministic chain. In cases where disaster is narrowly avoided, the discovery is no less sobering. A crack found during inspection prompts immediate action. Engineers scramble to assess fleet-wide risk. They calculate crack growth rates backward, estimating how long the defect has existed. Often, the answer is years. The aircraft has been flying on borrowed time, protected only by luck. Grounding a fleet is not just an operational decision. It is an admission. It acknowledges that the original understanding of the system was incomplete, that aging was underestimated, that confidence exceeded knowledge. This is a painful realization for organizations built on precision and control. The forensic investigation that follows is exhaustive. Every failed or suspect component is dissected. Metallurgical analysis reveals microstructures altered by service. Grain boundaries show signs of embrittlement. Inclusions, once considered harmless, are re-examined as potential crack initiators. Engineers revisit finite element models, this time adding complexity, real geometries, contact interfaces, thermal gradients, and degradation effects. Often, the models now predict what reality already demonstrated. Stress concentrations appear at overlooked features. Fatigue life shrinks dramatically when corrosion pits are introduced. Thermal stresses exceed adhesive limits under certain mission profiles. The math was always capable of revealing the truth. It was the assumptions that obscured it. From this process emerge new doctrines. Damage tolerance becomes more than a buzzword. Designs are revised to assume cracks exist from day one. Inspection intervals are shortened. Non-destructive evaluation techniques improve, capable of detecting defects measured in microns. Materials with slightly lower strength but greater toughness and corrosion resistance are reconsidered. Most importantly, engineering culture shifts. The myth of invincibility erodes. Engineers become more cautious about declaring margins sufficient. Test programs expand to include aging simulations, environmental exposure, and combined loading scenarios. The escape system is no longer treated as a static device, but as a living structure, evolving over its service life. Yet even as lessons are learned, new aircraft push boundaries again. New materials promise weight savings. New mission demands increase thermal and mechanical loads. The cycle repeats, not out of ignorance, but out of necessity. Progress requires risk. The challenge is to recognize where confidence ends and humility must begin. The ejection system remains a symbol of last resort, a compact embodiment of trust between pilot and machine. Its failures, rare as they are, remind the aviation world that safety is not a fixed achievement, but a continuous negotiation with physics. The margin between survival and catastrophe is measured not just in engineering drawings, but in microscopic cracks growing silently with every flight. As the fleet continues to age, the story shifts from design intent to material reality. What matters now is not what the system was supposed to do, but what it has quietly become after thousands of hours in an unforgiving environment. This is the phase where degradation turns from theory into inevitability, where the internal clock of failure begins counting down without any external sign. Inside the metal of an ejection seat rail, the crystal lattice is no longer pristine. Dislocations, tiny defects in the atomic structure, have multiplied under cyclic stress. Each vibration, each thermal expansion and contraction forces these dislocations to move, pile up, and interact. At grain boundaries, where crystals meet, stresses concentrate naturally. At a corrosion pit or a machining mark, and the local stress can exceed the average by an order of magnitude. This is where crack initiation truly begins. The crack is microscopic at first, smaller than a human hair, invisible even under casual magnification. It does not weaken the structure in any meaningful way yet. The aircraft flies on. The pilot ejects nothing. Confidence remains intact. But with every subsequent load cycle, the crack tip experiences intense stress concentration. At that tip, atomic bonds are stretched to their limits and then broken. The crack advances, not smoothly, but in tiny jumps, each one tied to a specific stress cycle. This process is governed by fracture mechanics, a discipline born from hard lessons learned in aviation and shipbuilding. The crack growth rate depends on stress intensity, material toughness, and environment. In dry, inert conditions, growth may be slow. In the presence of moisture, salt, or hydrogen, it accelerates dramatically. Fighter aircraft rarely enjoy benign environments. Naval operations introduce salt spray. Supersonic flight creates pressure differentials that drive moisture into crevices. Maintenance fluids leave residues that alter local chemistry. Hydrogen embrittlement becomes a silent accomplice. Certain high-strength steels absorb hydrogen atoms, which migrate to areas of high stress, reducing ductility and fracture resistance. The metal becomes less capable of deforming plastically at the cracked tip, making brittle fracture more likely. This phenomenon is notoriously difficult to predict and detect. The component may pass all inspections and still fail catastrophically under the right conditions. While metals degrade internally, polymers and composites tell a parallel story. The canopy transparency, exposed to ultraviolet radiation, undergoes molecular chain scission. Long polymer chains break into shorter ones, reducing toughness. The material becomes more brittle over time, less capable of absorbing energy during impact or explosive fracturing. Crazing networks grow denser, linking previously isolated microcracks into continuous paths of weakness. The adhesive layers bonding canopy to frames suffer their own fate. Adhesives are viscoelastic by nature. They flow slowly under sustained load. Over years, this creep redistributes stresses unevenly along the bond line. Areas once lightly loaded now carry more force. Add thermal cycling, and microvoids form within the adhesive. These voids coalesce, reducing effective bond area. When failure finally occurs, it often propagates rapidly, peeling the transparency away from its frame. None of this degradation is synchronized. Different components age at different rates depending on mission profile climate, maintenance quality, and even storage conditions. Two aircraft built on the same day can diverge dramatically in structural health after a decade of service. This variability complicates risk assessment. Engineers must plan for the worst case without knowing exactly which airframe it is. The most dangerous aspect of invisible degradation is how it masks itself behind normal behavior. The system still functions. The canopy remains clear enough. The seat slides smoothly during maintenance checks. There is no vibration anomaly, no sensor warning. Modern fighters are saturated with diagnostics, yet few of them monitor the health of structural bonds or crack lengths deep inside metal. Occasionally, subtle hints appear. A slightly higher force required to remove a seat during overhaul. A faint discoloration near a bond line. These clues are easy to rationalize away. After all, the aircraft is old. Whereas expected, the manuals allow for some degradation. And most critically, failures are rare. Statistical safety breeds complacency. The crack, however, is indifferent to statistics. As it grows, the stress intensity at its tip increases. This relationship is nonlinear. Early growth is slow, measured in microns per thousand cycles. Later, it accelerates dramatically. What took years to grow to 1 millimeter may take only weeks to grow to 3. This is the concept of remaining useful life, and it shrinks faster than intuition suggests. At a certain point, the structure enters a metastable state. It is still intact, still carrying load, but only just. The safety factor, once generous, has evaporated. Now, any unexpected event can trigger failure. A harder than usual landing. A thermal shock from rapid climb to altitude. A vibration mode excited by a specific combination of speed and angle of attack. The system is balanced on a knife edge. This is where hubris becomes lethal. The assumption that it has always worked becomes the justification for continued operation. Engineers and commanders alike rely on historical performance as proof of future safety. But fatigue does not care about history. It only cares about cycles. When the triggering event arrives, it is often mundane. Not a dramatic combat maneuver, but a routine sortie. The pilot may be practicing approaches, flying a training mission, or transiting between bases. The loads involved are within design limits, but they are enough. The crack reaches its critical length. Stress intensity exceeds fracture toughness. In metals, plastic deformation at the crack tip can no longer blunt the stress. The crack accelerates, racing across the cross-section at the speed of sound in the material. The failure is sudden and complete. There is no warning, no gradual loss of stiffness. One moment the structure carries load, the next, it does not exist as a load path. If this occurs during normal flight, the aircraft may show subtle changes, a new vibration, a slight misalignment. If it occurs during an ejection, the consequences are immediate and violent. The seat rail fails asymmetrically. The seat is no longer guided perfectly upward. It yaws or pitches as it accelerates, subjecting the pilot to complex G-loads the human body was never meant to endure. The canopy's role at this moment is equally critical. If its degradation has reached a tipping point, the explosive cord designed to fracture it may not propagate uniformly. Instead of a clean, predictable failure, the transparency breaks erratically. Large shards remain attached for milliseconds that matter enormously at ejection speeds. The airflow around the cockpit becomes chaotic, slamming debris into the ejection path. Milliseconds define survival. The sequencer does not know the structure has failed. It fires charges and deploys devices according to pre-programmed logic. That logic assumes a world that no longer exists. Drogue chutes deploy into disturbed airflow. Stabilizing fins encounter asymmetric loads. The pilot's spine, already compressed by acceleration, experiences lateral forces that exceed tolerance. In cases where the aircraft is still on the ground or in maintenance when degradation is discovered, the narrative shifts, but the lesson remains. Inspectors find a crack that should not exist. They trace its growth backward using fracture surfaces, counting beach marks like tree rings. Each mark corresponds to a load cycle. Together, they tell a story of neglect not in intent, but in understanding. The fleet is grounded. Engineers scramble to determine how close catastrophe came. Was the crack one flight away from failure? 10? 100? These questions matter not just for safety, but for accountability. Every additional flight flown unknowingly on a compromised structure is a reminder of how thin the margin truly was. Invisible degradation forces a reckoning. It exposes the limits of predictive models and inspection regimes. It highlights the gap between what is designed, what is tested, and what is actually experienced in service. Most uncomfortably, it reveals how human confidence can outpace material reality. The system that once embodied certainty now embodies risk, not because it was poorly designed, but because time and physics are relentless adversaries. Every aircraft carries within it the seeds of its own failure. The challenge of engineering is not to eliminate that truth, but to recognize it early enough to act. As investigations deepen, one conclusion becomes unavoidable. The most dangerous failures are not dramatic design flaws, but the quiet accumulation of small, ignored degradations. The enemy is not ignorance, but overconfidence. And nowhere is that lesson more stark than in the machinery designed to save a pilot's life when everything else has already gone wrong. The catastrophic sequence, when it finally unfolds, is mercilessly fast. All the slow, patient damage accumulated over years is released in a fraction of a second, converting stored elastic energy into violence. What was once a carefully engineered escape path becomes a chaotic collision between physics and human limits. The trigger is rarely spectacular. A compressor stall, a control surface failure, spatial disorientation at low altitude. The cockpit fills with alerts, but the pilot's decision is already made. There is no recovery window left. Training takes over. The ejection handle is pulled. In that instant, the aircraft transitions from a controlled system to an explosive one. Pyrotechnic cartridges fire, sending shock waves through the cockpit structure. The canopy system is the first to be tested. Explosive cords embedded within the transparency are designed to propagate a fracture pattern that fragments the canopy into predictable, low-mass pieces. Under ideal conditions, the fracture front races across the surface at precisely calculated speed, driven by uniform material properties and intact bonding. But the canopy is no longer ideal. Years of thermal cycling have altered its internal stress state. Crazing networks intersect the intended fracture path, deflecting it. Adhesive bonds that once constrained the transparency to its frame now fail unevenly. Instead of a synchronized shatter, the canopy breaks asymmetrically. One section clears instantly. Another hesitates, clinging to the frame for milliseconds that matter. As the seat rocket ignites, producing thrust equivalent to a small missile, the ejection seat accelerates upward at more than 20 times the force of gravity. The rails are suddenly asked to guide a mass that includes the seat, the pilot, survival equipment, and kinetic loads far exceeding anything experienced during normal flight. This is the moment the structure was designed for, yet it is also the moment when any hidden weakness becomes fatal. The cracked rail reaches its limit. Stress intensity at the cracked tip explodes as the rocket thrust loads the rail in bending and tension simultaneously. The crack, once creeping, now runs. It propagates across the remaining ligament of metal at near-sonic speed. The rail fractures completely, not cleanly, but jaggedly, releasing constraint on one side of the seat. The seat yaws violently. What was supposed to be a straight, vertical trajectory becomes a twisted launch. The pilot's body, already compressed axially by acceleration, is now subjected to lateral and torsional forces. The spine, vulnerable even in perfect ejections, is forced to absorb asymmetric loads it cannot redistribute. Vertebrae compress unevenly. Muscles and ligaments tear under stress they were never designed to handle. Simultaneously, the cockpit undergoes rapid decompression. If the aircraft was at altitude, the pressure differential collapses almost instantly. Air rushes outward, forming shock fronts that slam into the seat and the pilot. Loose debris from the canopy is entrained in this flow, accelerating to lethal speeds. Shards strike the helmet, the oxygen mask, the seat structure itself. Each impact alters trajectories further, compounding instability. The sequencer continues its blind execution. Stabilizing drogues deploy, intended to align the seat into the airstream. But the airflow is no longer symmetric. The partial canopy remnants and distorted cockpit geometry create turbulent wakes. One drogue inflates fully. The other is starved, fluttering uselessly. Instead of stabilizing the seat, the drogues introduce oscillations. Milliseconds cascade into chaos. The seat tumbles slightly, enough to misalign the pilot relative to the seat's protective geometry. Limb restraints, designed to pull arms and legs inward, engage under off-axis loads. Forces concentrate on joints. Shoulders dislocate. Knees hyperextend. The human body, evolved for endurance rather than impulsive acceleration, reaches its tolerance limits rapidly. If the canopy failed to clear completely, the seat may strike residual structure. Even a glancing blow at ejection velocity is catastrophic. Energy that should have been spent on separation is instead absorbed through deformation and impact. The seat's orientation degrades further. Parachute deployment timing, calibrated to altitude and speed, now occurs under abnormal attitudes. When the main parachute deploys, it is no longer guaranteed to do so cleanly. Line twists develop instantly. The canopy may inflate asymmetrically, producing violent opening shocks. In the worst cases, the parachute collides with the seat or the pilot, entangling lines around limbs or equipment. The difference between a survivable descent and fatal trauma is measured in degrees of misalignment and milliseconds of delay. From the outside, the sequence appears as a blur. Observers may see a flash, a plume of smoke, fragments arcing away from the aircraft. They may assume the system functioned as intended because an ejection occurred. Only later, when wreckage is recovered or medical reports are written, does the truth emerge. The system fired, but it did not protect. In accidents where the aircraft impacts terrain immediately after the ejection command, the failure can be even more unforgiving. A seat launched with compromised guidance may not clear the aircraft's tail. Impact occurs within fractions of a second, leaving no chance for parachute deployment. The distinction between system failure and insufficient altitude becomes blurred, masking the true cause. In cases without loss of life, the aftermath is still violent. Pilots survive with severe spinal injuries, crushed vertebrae, nerve damage that ends flying careers permanently. The seats saved their lives in the narrowest sense, but failed in its deeper promise, to preserve the pilot as a functioning human being. For engineers and commanders, these outcomes raise uncomfortable questions. Survival alone is not the metric of success. Integrity is. Every catastrophic sequence forces a reckoning with the assumptions that shape the system. The ejection seat did not fail because it was poorly designed in isolation. It failed because its environment aged beyond the envelope imagined at conception. The violence of physics exploited microscopic weaknesses accumulated quietly over time. In forensic reconstructions, investigators replay the sequence frame by frame. High-speed camera data from tests is compared to wreckage deformation. Flight data recorders reveal timing discrepancies measured in milliseconds. Medical findings are correlated with load paths inferred from broken components. Slowly, a coherent narrative emerges, stripping away comforting myths. What becomes clear is that catastrophe is not a single event, but a convergence. Degraded materials, altered geometries, aged adhesives, and rigid sequences all align in a narrow window where failure becomes inevitable. The system does not collapse randomly. It collapses precisely where physics dictates it must. This phase, the catastrophic sequence, is where arrogance is punished most harshly. Not moral arrogance, but engineering arrogance. The belief that margins are permanent, that successful history guarantees future safety. In this moment, the aircraft, the escape system, and the pilot are reduced to interacting masses and forces, indifferent to reputation or intent. The violence ends as abruptly as it begins. What remains is wreckage scattered across terrain or sea, and a single, unavoidable question: how did a system designed to save lives become part of the mechanism of destruction? Impact and immediate aftermath expose the full cost of failure, not only in human terms, but in institutional shock. Whether the event ends in a fatal crash, a severely injured pilot, or a narrowly avoided disaster discovered during maintenance, the consequences ripple outward with brutal speed. When an ejection goes wrong in flight, the aircraft itself often becomes irrelevant within seconds. Uncontrolled, it impacts terrain or water, disintegrating under kinetic energy orders of magnitude greater than any structural margin. Wreckage scatters along ballistic paths that investigators later map with precision, each fragment marking a data point in a timeline measured in milliseconds. The aircraft, once a multi-million-dollar expression of national power and engineering pride, is reduced to twisted metal and burned composites. If the pilot survives, the immediate scene is dominated by medical urgency. Parachute descent ends in a hard landing, often uncontrolled. Rescue teams reach a body bearing the unmistakable signature of abnormal ejection loads. Spinal compression fractures, burst vertebrae, pelvic injuries, torn ligaments, and nerve damage. These injuries are not random. They map directly to asymmetric forces experienced during the escape. Doctors understand quickly that this was not a clean ejection. For the pilot, survival is only the beginning. Even in the absence of paralysis, chronic pain and reduced mobility are common. Flying careers end instantly. Years of training, experience, and tactical knowledge are lost to a single mechanical truth. The system worked, but not correctly. For air forces, this represents not only a human tragedy, but a strategic one. Highly trained pilots are irreplaceable assets. When the failure is discovered on the ground, the shock is different, but no less severe. A cracked seat rail found during an overhaul, a delaminating canopy bond exposed during inspection, triggers an immediate grounding order. Aircraft scheduled for operations are pulled from the line. Missions are canceled. Commanders demand risk assessments that engineers cannot yet fully provide. The realization that a fleet has been flying with latent, potentially catastrophic defects produces institutional paralysis. The question is not whether to act, but how far to go. Ground one aircraft? A squadron? The entire fleet worldwide? Each decision carries operational, political, and financial consequences. Yet hesitation is dangerous. Once a failure mode is known, every additional flight becomes a gamble. Maintenance units are flooded with directives. Emergency inspection procedures are written and disseminated in days, sometimes hours. Non-destructive evaluation teams deploy ultrasonic probes, radiography, eddy current sensors, searching for cracks measured in tenths of a millimeter. Canopy transparencies are examined under polarized light to reveal hidden crazing. Adhesive bonds are tapped, peeled, sampled. The results are rarely comforting. Variability emerges immediately. Some aircraft show no defects. Others show early signs. A few reveal cracks alarmingly close to critical length. The fleet is heterogeneous in its degradation, reflecting differences in mission profiles, climates, and maintenance histories. This makes blanket assurances impossible. Engineers cannot say with confidence which aircraft is safe tomorrow. In parallel, accident investigation boards assemble with forensic discipline. Wreckage is recovered when possible, even from hostile terrain or deep water. Each fragment is cataloged, its position recorded. Seat components are reconstructed like skeletal remains, fractures aligned to understand load paths. Metallurgists examine fracture surfaces under scanning electron microscopes, identifying fatigue striations, brittle cleavage, or corrosion-assisted growth. These microscopic features tell the true story. Beach marks reveal the rhythm of crack growth over time. Inclusions, once dismissed as acceptable, are scrutinized as crack initiators. Coating failures are traced to specific chemical exposures. Adhesives are tested and found to have aged beyond their original specifications. The failure is no longer mysterious. It is inevitable in hindsight. What follows is crisis engineering. Design authorities, manufacturers, and regulators converge to define corrective action. Temporary fixes are proposed: reduced flight envelopes, lower speed limits, restrictions on ejection conditions. Permanent fixes require redesign. Seat rails are thickened, geometries softened to eliminate stress risers. Materials are changed to favor toughness over ultimate strength. Protective coatings are improved. Inspection intervals are shortened dramatically. For canopy systems, solutions are equally invasive. Transparencies are replaced preemptively. New bonding agents are qualified with better resistance to ultraviolet radiation and thermal cycling. Explosive fracturing systems are redesigned to tolerate material variability and partial degradation. Sequencers are reprogrammed to adjust timing dynamically, acknowledging that real systems do not age uniformly. All of this takes time. During that time, capability is lost. Aircraft sit idle. Pilots are reassigned or grounded. Allies question readiness. Budgets strain under the cost of retrofits and lost flight hours. Public confidence, when accidents are visible, erodes quickly. Questions reach political levels. How could this happen? Why was it not caught sooner? The answer is uncomfortable. It lies not in negligence, but in the limits of prediction. Engineering models are abstractions. Certification tests are snapshots. They capture the aircraft at birth, not at middle age or old age. Aging, especially in complex, multi-material systems like modern fighters, is nonlinear and difficult to bound. The escape system, designed as a last resort, becomes a victim of the same aging mechanisms as the airframe it inhabits. In cases where lives are lost, the aftermath extends into memorials and reforms. Names are added to lists of those killed not by enemy action, but by mechanical reality. Training syllabi are updated. Emergency procedures are re-examined. Yet the deepest changes occur quietly in design offices and standards committees, where assumptions are rewritten. Investigators often conclude that no single action would have prevented the failure. Instead, a chain of small decisions and overlooked interactions aligned perfectly. Inspection thresholds set conservatively, but not conservatively enough. Materials chosen for performance rather than longevity. Environmental effects underestimated. Safety margins consumed slowly until none remained. The immediate aftermath, then, is not closure. It is disruption. It is the moment when confidence collapses and must be rebuilt from evidence rather than belief. Every grounded aircraft, every injured pilot, every fractured component becomes a reminder that safety is not static. In the silence after the crash, or the tense calm of a grounded hangar, the illusion of invincibility finally dies. What remains is a harder, more honest understanding that even the systems designed to save lives are themselves vulnerable to time, stress, and human assumption.